In my previous video, Nerds108, I arrived at this design for a selective amplifier. It is an experiment with 20 crystals in parallel here. And as it turns out, when I use this as an amplifier to filter the signal from a Wenzel oscillator, performance is extremely good. I don't see any noise added at 1 Hz offset, and at 10 Hz offset the signal from the noise from the Wenzel oscillator is reduced significantly, and the noise added by this amplifier is very low. But you can see the details in the previous video. Now I'm going to make an amplifier to lower the impedance. I have 6 volts peak to peak here, but that is at an impedance of about 600 ohms. So I will replace these things with an amplifier. As a first thing, I want to know exactly what is the impedance in this point when I disconnect the transistor and just look at this circuitry. Because I want an amplifier with the same input impedance as I have with the current setup. Here is the input impedance I want. 530 ohms and 4.37 microhenries. I have added this amplifier. First a step-up transformer, 8/3. There is a 560 ohm resistor to provide the correct impedance for the previous stage. Something to prevent oscillations. Maybe not this one was necessary. And then a 1-to-1 transformer to give low impedance, and then a transformation to half the voltage, and then resistors and the capacitor to provide 50 ohms and 30 milliwatts output power. The close range performance is very similar to what I observed in the previous video without this amplifier. 10 Hz minus 152.7 or so. 20 Hz minus 160. That's here. And here is the PM2060. And I see no differences at 1 Hz. It is minus 120.6 with the cursor position. Here, just at 10 Hz, there is a little hump, and the cursor says minus 151.7. But if I make a straight line, I come half a dB below that, perhaps. And 20 Hz, minus 161, or even 162, but it's a little bit too noisy to try to be precise. But there is a big difference out here at 10 kilohertz and above. Previously I could not see the noise, but now I see it clearly at minus 187 about. I have disconnected the amplifier, the stuff down here, and restored the output directly from the source follower through the coil and the capacitor and the resistor. The result was unexpected to me. It was no better than what I saw with the amplifier also. I decided I have to check my memory by looking at old screen dumps. This one is from the 1st of September, and it shows the result I have now, about minus 189 or 190. And this is a recording over 9 hours, so it has very good statistics. So where did my memory come from? It is this recording. It is with a cable of about 90 degrees. Actually, the phase shift was 82 degrees, connected in front of the DUT2 input of the PM2060. I am well below specifications. They say above 10 kilohertz minus 180. And now, with that phase shift, many circles showing that I should not trust the result. So I have restarted measurements now with a 90-degree phase shift. I have left the box open and added a quarter-wave cable at the DUT2 input. This box contains low-pass filters designed to pass 10 MHz but not overtones from it, and to present 50 ohms to the PM2060 on all frequencies well up in the VHF range. That explains why the result at 1 Hz offset is not so good. It is minus 112 dBc per Hertz. But already at 10 Hz, the effect of having no lid on the box is small. I see minus 152. And then, most important, above 100 kilohertz, I see minus 195. So this is significantly better than what I saw without that phase shift between the two DUT inputs. Now I don't know if one or the other way of measuring is incorrect, so I will look at other ways of studying the flat noise floor. I have attenuated the signal from the Wenzel oscillator by 120 decibels. Still with the output from the source follower, I have connected a low noise amplifier to the output. It has 50 ohm input impedance and is a low noise thing. And then one more amplifier to have sufficient level to not have any contribution from the noise of the Perseus itself. I have calibrated Linrad to show minus 120 decibels, 0.03 here. That is for the carrier, with the S means signal in front of it. I can see from the waterfall that the noise floor is reasonably flat. It has some periodic structure, but it's very weak. That is due to the digital filtering. Anyway, I can now read the noise floor in dBc per Hertz. It says minus 191. Here, 191.05. And that is phase noise plus amplitude noise. And they should be equal in amplitude because this should be white noise from the amplifiers. So it means I read minus 194. And that is pretty close to what I saw when having the 90-degree phase shift between the DUT inputs. As a sanity check, I have connected a 50 ohm dummy load on the input of the low noise amplifier. And this is one of my best dummy loads. It is very close to 50 ohms. And that is also the output from the box I have. The change in the noise floor is very small, so I increased the bandwidth to see it better. Here is the noise from the dummy load, and I measure it over this time interval, and it says minus 187.22. Now calibration has changed, but I want to see the difference when I remove that dummy load now, and then I connect my selective amplifier here. And as you can see, it seems to be a trifle higher, but the difference is really very small. Which means that most of the noise originates in my low noise amplifier. So out from my box is room temperature noise, nearly only. So the sideband, the noise floor is well below minus 195 dBc per hertz according to this. If I measure this range, I see minus 187.615 and before minus 187.22. So the difference is 1/10 of a decibel or so. Very, very small. The Wenzel oscillator is inside this box. There is a balloon on the PCB, and now I added 40 decibels of attenuation here. I have added one more balloon at the other end of the cable from the other room. Signal leakage should now be eliminated. I have set this attenuator to 60 dB for a total of 100 and will calibrate for that. So now the carrier is calibrated and I will step the attenuator in steps of 10 dB to check that I can have significantly more than 120 without signal leakage. Well, as it turns out, I cannot. 100 decibels, 110 is okay, but 120 and above that, then there is a problem. But I have calibrated on the signal which is 100 decibels down from the normal carrier level, so this calibration is accurate now. The previous calibration at minus 120 was probably not okay at all. I have now clicked at the noise floor 20 kHz up. And you can see one interesting thing. The noise that surrounds the carrier is pretty strong. And that's the noise from the crystal, probably thermal noise. I will go back to that after switching off the Wenzel oscillator, because that is an interesting aspect why the white noise can be so low. The noise floor 20 kHz up is minus 183.3. Means phase noise should be minus 186.3. That's significantly higher than what I found before. I have connected the 50 ohm dummy load, and after moving the curve I have the result from the box, now 183.40. And here minus 187.40, 47, and here 40. Well, the difference is 3 decibels. So it means the noise from the box is minus 187, equally strong as the noise of the system that I see with the 50 ohm dummy load. So minus 187, and then add 3 decibels because I am only interested in the phase noise. So what I see is minus 190 with this method, and give or take 1 or maybe 2 decibels. Anyway, it seems that the method of measuring phase noise with a 90-degree cable is not okay. It gives an over-optimistic picture. And maybe I can understand it, because the cable is not only a phase shift, it's a time delay. And if I imagine a very long cable, I realize that high modulation frequency, they will not be correlated if they are separated in time. So maybe that's the effect I see already at a quarter wavelength cable. So I will remove that and go back to the original kind of doing these measurements. I have switched off the power supply for the Wenzel oscillator. There are big capacitors, so it takes some time before it becomes quiet. But you can see now that the filter has been correctly tuned. I don't have a tuning capacitor anymore, but it is fixed capacitors and I have arranged them to be at the proper frequency. And what I'm interested in now is what is the level on the peak here and what is the level well outside. Because this is the thermal noise of the crystal, but far from the frequency the thermal noise is much lower because the impedance is much lower, well away from resonance. And it looked like more than 10 decibels. I have moved 100 Hertz upwards and the noise floor is 14.4 decibels lower. So that is part of the reason why the noise in the flat floor is so low. And the noise floor here, 100 Hertz up, is equally strong as the noise from my low noise amplifier. So I should add 3 more decibels. So I have 17.4 dB advantage from this. I am now running at full power without the quarter wave cable for the DUT2 input. And in the line between my selective amplifier and the test system, I have added this crystal filter for 10.7 MHz. That will present a 50 ohm load on the cable, which will be mismatched, of course, at 10.7 MHz, which doesn't affect anything. And at the output of that crystal filter, I have this low noise amplifier and the Perses. The PN2060 looks normal. It's a very short time. But the Leanrad, that's the interesting thing. You can see there is a significant signal coming out at 10.7 MHz, and I have centered a fairly narrow filter on the center of that passband. And here I have a noise floor, and I can run a little bit slower to get better accuracy on it. So this is the noise floor I have. And then I reduce this power. Now 40 decibels of attenuation. And the interesting thing is to see, did the noise floor change or not? And it says, well, there is a 0.1 dB difference. And that could be just statistical uncertainties. Now it is the same. And it varies by 1/10 of a dB up and down. So this was to verify that the amplifier, the noise, the white noise of the amplifier is not affected by the signal. There could be quieting if the amplifier is saturated, but there could also be noise generated by some whatever mechanism if the amplifier goes into saturation. So this verifies that the measurement should be okay. Now that I know that the noise floor does not change when I add the full carrier, I have attenuated the carrier by 15 decibels. And now I expect the PN2060 to give me an accurate reading of the phase noise And to get the real performance at full signal level is to add 15 decibels to what comes out here. And it seems to be about 174. I will wait a little while. Now I get a good measurement of the flat noise floor. It is at minus 174 dBc per hertz. Or maybe 175 if I wait long enough. But I go for minus 174. And then I had to add the 15 decibels, means 189. And that should be pretty accurate. And it is in agreement with what I found in the other ways also. So minus 189 dBc per hertz when this unit works as an amplifier. And it should not be any difference when it works as an oscillator. Except that perhaps more stages that I will add some extra noise. We will see. One obvious thing I can do is to remove this resistor. I don't know if it matters what the impedance loading the source follower is, but probably I should get a little more signal and therefore a little better phase noise at large separations. Now the phase noise is at minus 175, 1 decibel lower. So what I have found is now minus 190 dBc per hertz for my selective amplifier without that resistor. For the performance close to the carrier, I will restore full power. In this paper there is a statement. These noise levels represent some of the lowest ever reported at these frequencies. And that is minus 182 for 10 megahertz for the phase noise. And the amplitude noise is reported as minus 191. And I think my experiment will have the amplitude noise at minus 190 also, because this is white noise from the amplifier. When I removed this resistor, as it turns out, this amplifier ran into saturation. And obviously that didn't have any consequences for the sideband noise I have observed. So what I did is to put a single turn here and then a 90-degree phase shift and to the input. And that turns the unit into an oscillator. To test this, I made something very ugly here to shift the phase properly. The box is open and this is going to pick up interference. The phase noise I see was of course rather ugly, but not entirely uninteresting. At large offsets, the floor here is at about minus 187, and there is a lot of interference, of course. At close separations, 10 Hertz, I see minus 146, and the shape is peculiar. At 1 Hertz, this is minus 112. And then at closer separations, the noise goes up rapidly. And I don't know what that is. Maybe vibrations, maybe infrasound, maybe some electronic noise, I don't know. I will make a proper version of this, put it inside the box and put the lid on. Now the phase shifter is within the box and the lid is on. And I have been running for 1.5 hours. And the result is a little bit odd.
At 10 Hertz I see minus 155, but at 1 Hertz I see minus 115. And at 0.1 I see minus 53. And that is very far from what I would like to see. I have been running Linrod in parallel, and I can see at 10 Hertz minus 156 where the mouse is now. But the imaginary part is at minus 158. So statistics is not good enough. Now, there has been a problem. I had a power outage here for about 1.5 hours. And then when I started, things were cooled and the PLL was not locked. And channel 2, the phase locking, has failed. You can see it goes up and down and it has not locked properly. I have set the fastest time constant, and that means that the slope is much bigger and that the coverage is a little bit larger. Then I have adjusted the frequency and I expect it to lock now. I shift the traces vertically by clicking on the star up here, and then I expand the scale by a factor of 10 from 0.5 to 0.05. Note how slow it is. It is 200 seconds for each division on the horizontal scale. And yet this is the fastest time constant I have. Here I have switched to a 4 times larger time constant in channel 2. And here the same in channel 1. It was originally in the fastest time constant, and I think we can see now it is going to be calmer than it was here, because there is the noise from the rubidium source. And now I can center the tracks again and expand the vertical scale by a factor of 5, 0.01. Then I wait for a while. The frequencies differ by about 0.8 millihertz. There is not much correlation in the movements for the two channels, which would be the consequences if there was an instability in my new oscillator. So the uncorrelated movements in frequency, here you had something in channel 1. That is problems in my reference oscillators. And there is a new phenomenon I have never seen before. These short spikes of about 0.2 millihertz that occur regularly in channel 2. And when I look in the PN2060, I can indeed see here that the frequencies differ by 0.7 millihertz approximately. Well, they are similar in frequency, and if I wait long enough they will go up and down around a common frequency that is defined by the rubidium oscillator. But now it's time to restart the PN2060, I think. And maybe it's better to not use 4096 for the FFT. It takes a long time. I start with 1024 instead. That degrades performance at high offsets, but I want to see what happens at close to the carrier now. Now I restart here because I want to see the Allen deviation. Here something has happened. Now I have a strong correlated signal between the two channels. So it is probably originating in my new oscillator. Or something has happened to my system. I don't know. If I look at the PN2060, I see a strong peak here for that signal and its overtones. Well, this nice sine wave correlated structure were caused by the Wenzel oscillator. Somehow there is RF on the screen, a little bit of that, so I have disconnected the cable, the coaxial cable, and that changed the DC current return. So I had to increase the supply voltage to my new oscillator by 100 millivolts. And now it looks normal again. I have swapped the power supplies between my two reference oscillators, those in channel 1 and channel 2. And these frequency jumps of about 0.2 millihertz still occur in channel 2. So they did not originate in the power supply. And whether the curves are more or less noisy now as compared to what it was before here is hard to judge. It would require a more careful study. Maybe channel 2 is a little less stable, and I restart measurements to see what happens in the long time again, and also for the Allen variation. Allen variation, the yellow trace is the correlated between the two channels, and up here at several hundred seconds it reflects the drift with time because of temperature presumably, and both drift the same way, of course, because both are phase locked to the rubidium source. So my reference oscillators are very stable over long times. But to see what differs between the channels, it's better to look at the Hadamard deviation. Looks like this. And you can see at 150 seconds or so, the channel 1 oscillator is about 1 order of magnitude more unstable than the channel 2. And that we can see clearly in the frequency versus time. But on the other hand, at about 5 seconds, channel 2 is more noisy than channel 1 by a factor of 3 or so. And you can see these various phenomena that occur. And I haven't seen them before. It's something new. Maybe something will fail, so it will be easier to find what the problem is. 13 hours have elapsed. I have good statistics. And the result is rather interesting. At 10 Hz offset, I see minus 157, which is extremely good. But at 1 Hz offset, it is minus 122, which is good, but not in relation to what I had down here. And the slope is very steep. So at 0.1 Hz, I see minus 79, which is not good. And at 0.01 Hz, only minus 40 or 37 or something. So there is a problem with this oscillator, and I think it is the source follower. The gate-to-drain capacitance may vary a little due to flicker noise in the transistor, changing the current just a little. And since that capacitor is up-transformed from the crystals, very small changes will have an effect on the phase shift or on the frequency. So it produces phase modulation. It should grow like this very rapidly when one approaches the carrier. Linrod has been running in parallel, and I can read at 10 Hz minus 156. So it is in agreement. What I was interested in is to see what has happened to the amplitude modulation. And it is weak. I can have both of them. And I see they are a little correlated, but that disappears at about 6 Hz, because at that offset the amplitude modulation is not properly evaluated. It is below the imaginary part. I was thinking perhaps that the problem at very low offsets were caused by the limiter, but that should affect AM and phase noise in a way so they should be strongly correlated. And that's not what I see. So I think the idea of the source follower is the reason for the not so good performance I see close to the carrier. Here is the entire circuit diagram on a single sheet of paper. As before, the output is from 2 turns on this transformer through these components to make 50 ohms. And I have added from a single turn a phase shifter and then connected to the input here to make an oscillator. And one more thing, I have added a capacitor of 470 pF from this point to the drain of this transistor. That is to put a voltage here which is the same as the voltage on the base. Bootstrap configuration, I think they call it. This makes the influence of the capacitor from here to here smaller. Previously, this was coupled to ground through a capacitor. But now this is following up and down together with the base. This change has made a difference. Firstly, the frequency is now 40.5 Hz above 10 MHz. Previously, it was 37.8. So the frequency is up by nearly 3 Hz. The effect of the capacitor is smaller to the extent that it drifts the frequency upwards by nearly 3 Hz. And then, when I look at the phase noise, I see at 1 Hz now minus 125, which is probably a kind of record for crystal oscillators. And at 10 Hz minus 155. But the curve is pretty noisy, even though it has been running for 3 hours now. At 0.1 Hz, the noise is high. I can compare this with an old recording from the Wenzel oscillator, which I have here. You can see 93, and now it is 10 decibels worse. Here, this is much better than the Wenzel, and here it is very much better than the Wenzel oscillator, and also so for all the other higher frequencies. But there is one problem. When I was doing that investigation on the PLL system, I forgot to go all the way up to the longest time constants. So at the moment I have on position 2 on the switches. They go from 0 up to 6, where I usually have one of them. So I will stop here and make a test on the Wenzel oscillator, because the old measurement on the Wenzel oscillator may have been while I still had the flow of 2 amplifiers with the same power supply after the hybrid in the correlation system. I have connected the Wenzel oscillator, and now I compare with the old recording I had. And you can see here that was because the amplifiers with a common power supply, which I have eliminated and gained a couple of dB. But here the noise is far too high, about 10 decibels. And I guess this is because of the time constants of my phase locking. I have had Linrad running in Allen mode, and this is what the frequency versus time looks like. I will change the time constants to make them much larger. And that is what I normally have had before. It was a mistake leaving them in position number 2. I have increased the resistors in the RC filters of the PLL from 4 kilo ohms to 100 kilo ohms. That's a factor of 20 for the RC time constant. And if you look at channel 2, the red trace here, and how it looks here, there seems to be a visible difference. And what will happen with channel 1, I don't know. I will have to wait for a while to see if it oscillates or whether this is something that has to do with my changing of the time constant, because I had to change the frequency a little bit also. Here is what I have now, and here is my old result, and there are marked differences. Look at the imaginary part down here. Now it is like that. So my reference oscillators have degraded. So the correlation has to be work much longer to come down. But performance is better all the way down to 1 Hertz. And that's because of that mistake I had feeding 2 amplifiers with the same power supply. When it comes to my reference oscillators, I have been running Linrad in parallel, and you can see the big difference in noise between channel 1 and channel 2. This is something that has happened, and I don't know exactly when. Maybe when I change the frequency for my new frequency after that frequency shifter introduced recently. I will look into this and try to fix my system before I go back to study the new multi-crystal oscillator. Because presently, with this performance degradation I would have to wait several days to see the performance at 0.1 Hertz. And that's unreasonable. I have cleaned the contact surfaces on the trimmer capacitors that is used for setting the frequency of both oscillators. I have also added fixed capacitors to have the tuning capacitors very close to the minimum capacitance. That is to reduce the current through the potentially noisy contact surfaces. This has improved a little. I can now see the noise of the Wenzel oscillator at 0.1 Hertz, here at minus 93 Hertz. and it's 10 hours measurement time with 38-hour averages here. I can also see maybe the noise at minus 44 with 2 averages only. But some time ago here, this is only 19 averages, and I see the noise at 93, minus 93 very clearly. Note the imaginary part is down here at minus 98 or so, while now the imaginary part is at about 95, despite twice the measurement time. So I have a problem. But at 0.01 Hertz, here I have 2 averages and I see minus 43. And in the old I had only 1, but it was above minus 40. So whatever causes the problem does not cause a much worse problem at even longer times or closer to the carrier. And the measurement of the Allen graph here and frequency versus time, you can see channel 1, the green trace, is very noisy in a longer time scale, and suddenly there is a frequency jump. So my equipment isn't really good enough to do measurements on my latest experiment. I have replaced the channel 1 oscillator. This one is a little bit better. I can see in the Allen graph it is almost 10 to minus 12 at 10 seconds, which corresponds to 0.1 Hertz. But in the meantime, something has gone wrong with the channel 2 oscillator, which is at 4 times 10 to the minus 12. And you can see here how noisy it is. And that means that I cannot see the 0.1 Hertz noise well. It should be 93, but it shows 90, and that the imaginary part is at the same level as the signal. I can see the noise at 1 Hertz, and the signal source is the Wenzel oscillator. So I will try to find out what is wrong with the channel 2 oscillator. I have replaced all the capacitors that set the frequency, because I thought maybe they have become unstable. I have been too close to these polystyrene capacitors with the soldering iron, so I can see that the outer layer of polystyrene has melted, and that is a problem in 3 of them. In total there were 5 capacitors, and here is the arrangement for those 5. I had to get 16 PF here, and I had 3 PF to the varicaps and 39 PF in parallel with the varicaps. I have selected components slightly differently, but it ends up with the same number of capacitors. And this time I've been very careful to not come too close to any of them with the soldering iron. As it happens, I had set the frequency slightly too high, so the PLL could not lock. You can see here how it tries, but it cannot come close enough to the correct frequency. So I have adjusted the frequency, and now it is locking, as you can see here at the end. And I have changed the vertical scale, and as you can see, the locking of the channel 2 comes in slowly. Now the PLL has locked, so I restart the Allen graph. It does not look promising. As you can see here, this is a problem with the oscillator. But I want to see what the Allen graph looks like. and I restart the PN2060 also. It seems changing those capacitors did not solve the problem. The channel 2 oscillator is still very unstable, and channel 1 is also not stable, but there is a significant difference, and that is that instabilities in channel 1, they are at very long times, but at 1 second channel 1 is much better than channel 2, and at 10 seconds there is still a significant difference. And one can see that with the sharp structures here, while this is smoother, but the slow variations are much bigger, and they are harmless. I have replaced the PLL by a stable signal from a power supply. That was at this time, and after that the frequency instabilities look pretty much the same as with the PLL. And the PLL has a long time constant, so it shouldn't affect these fairly rapid variations. So, problem is elsewhere. Beneath this cat pillow, I have a tiny PFA. This is a very lightweight pillow, and the purpose of this is to prevent circulating air from changing the temperature of this tiny PFA. It is attached to this thick aluminium sheet, and there is thermal material, the same we use when cooling transistors, a thin thermally conducted, I think, plastic material, and it's by these metal clips firmly pressed onto the aluminium. That is to keep the temperature as constant as possible when it goes from idle mode to working full normal mode. That causes a small temperature shift. I want that to restore to the temperature of the big aluminium as fast as possible. And there are ground connections here for the USB and for the signals, and there are ferrites here to prevent RF from coming wrongly into the unit. So this is a fairly well thought out setup, I think. Then there are attenuators, and they are fed from these boxes which contain bandpass filters for 10 MHz, because the tiny PFA is sensitive to overtones. While the oscillator is still running in normal fashions with a normal signal level into the PN2060, I check the signal level on the output connector from the box, and I see on the oscilloscope here .62 volts peak to peak. And I need to remember this for the future. The USB cable from the tiny PFA goes to this filter, big capacitors, before the USB continues to the computer. The signal from the Wenzel oscillator, first an attenuator, and then I split it in two, and the two cables are carefully routed together to have the same temperature change, and then one goes through the box and the other goes through this BNC to BNC, and then they are together again, going to the filter boxes here, and then to the tiny PFA. As a first step, I verify the setup, because it's very critical. I use this free BNC input, and then a wire that I will connect to this other BNC, which is normally the feedback output, which I no longer use because I have an internal coaxial cable which is now disconnected here. And this thin wire is the output from the amplifier, which I also have disconnected now. So I will connect this blue wire to the BNC to have just a straight wire inside the box. Just like this. I set the signal level to 6 dBm. That seems to be the level for optimum performance of this unit. I have set the signal level to 6 dBm in both channels. That gives the best result as far as I have understood. And then I click on measure and then null the frequency. I already did that, but that's the procedure. After having nulled the frequency, I have to go to output and log to frequency, and then to output and log to unwrapped phase again. There is a bug in the firmware so this change of the output is necessary to get the correct results after having nulled the phase. And finally, I put the cat pillow back to prevent changes in temperature due to moving air when I move around in the room. And now I start measurement. And I look at phase versus time. Original, like this. I have opened an old file containing the measurement of nothing, and you can see the result I have now is significantly more noisy. So I will put the lid on the box and screw it tightly. That destroyed the Allen deviation completely, and it's obvious when I look at the phase difference. Here you can see putting the lid in place, tightening the screws, and then I'm finished. So I have to restart measurement. And then I remove this ugly and this is the old measurement of nothing. And here is the new with the wire, and it takes some time before things stabilize, so I have to wait. There are different phenomena with different time constants working in different directions. So this fairly fast thing, and then comes something which is slower and lasts longer. And I don't know what will come next, but I will have to wait. After 3 hours, the frequency is stable, so I stop measurement here. I select the current measurement, and then I zoom into the data that is not good yet. Let's say like this, and then the edit function, and remove selected, like that. And now I have the flat region, so I can look at the Allen variation or Allen deviation here, and it looks reasonable. Very small differences from the old that I had since I don't know when.
The first amplifier stage is a BF240 in common base configuration. I have disconnected the crystal from the emitter and connected the signal from the Wenzel to the emitter through a capacitor to keep the same biasing, the same current. And I feed it through a resistor network that is an attenuator that gives me the proper output signal, which I measure here, the same place as before. And I see 2.62 volts, just a trifle above that. I have a 50 ohm dummy load on the other side of the connector to load the normal output with 50 ohms as it should be loaded. The output from the limiter is the signal I send into the tiny PFA, and it looks like this. It is a little lower than the input signal to the box, but this is the level that gives the appropriate output power when connected to the input. When I look at the crossed diodes that constitute the limiter, I can clearly see that they are limiting the amplitude. I put the lid back on and look at the tiny PFA. I cannot get more than 5 dBm from the limited output, but this will not make a significant difference to the result. And I check this and null the phase from 13 nanoseconds, which is quite a lot. And now it is 2, and now it is 0. And then I have to correct the bug in the firmware, so I have to go back to frequency and then to unwrapped phase, and then back with the cat pillow. Initially, the Allen deviation looks very ugly, and that is for obvious reasons. If I look at the phase difference, you see it is very far from stable. So I have to wait. After 1 hour 45 minutes, the phase shift through the amplifier is reasonably stable. So I stop measurement here and go to and select the first part. Like this. Remove that. And then I can see how noisy the phase shift is. But I want to remove the frequency drift. That is, subtract the global linear frequency drift. And here is the noise. And then I can look at the Allen graph and see this is the problem I have with the amplifier. Here is the circuit diagram. This unit was described in Nerds 76 and 77. As I can see, I used it then at a much higher signal level, plus 18 dBm. So I will increase the input signal to get that signal level out. With 5 volts on the output, here, what I have on the limiter diodes here looks like this. It's the same level as before, almost, but the clipping is much harder. And the level at the limited output is about 3 dB higher, so I attenuate to get back 6 dBm as the level on the B input.
The phase shift through the amplifier chain, including the limiter, is drifting continuously over 7 hours. But I can cut out about 1 hour, the last hour, and flatten it to see what is the noise. Well, the noise does not seem any better than it did at a lower power level. And I can check the Allen deviation. As you can see, it is actually worse, which is not unexpected, I think. I just found that when looking at the voltage across the crossed diodes in the limiter, I had the 20 MHz bandpass filter enabled. And here is what the signal really looks like. I have disconnected the limiter by cutting here. And now I'm measuring the signal that comes out here. I had, of course, to increase the attenuator in the B channel of the tiny PFA. What I see is quite unexpected. I have a region here, I can zoom into it, which looks quite promising. But then, when I come to the flat region here, it looks very odd. It jumps between two states, and I don't know what this might be. I have edited the phase data and selected the first part and the last part. In the beginning, when it is changing fairly rapidly, first part, red, it has very little high frequency noise, and then it is not too bad. And the other one, the last part that jumps up and down between two different states, has a lot of noise all the way. So I have to find out, why is it jumping between two states? And when I zoom into this, I can see that at 60 milliwatts output, it was jumping between two states the same way, although there was some more problems that are not so visible now, and therefore it is more clearly seen. There is jumping up and down by about 1 vertical scale division, both in this blue and the green trace, but not at the lower power level. I have removed all traces except one and started a new measurement, and now I can see it jumps up and down. So I try to see whether this continues when I open the box. Of course, there is a big phase shift when I open the box, and there is then a continuous drift because temperature changes. So I will have to wait for a while to see if I can see something with the box open. Without the lid, the phase shift through the box is very much noisier than I can accept when I look for this shift between two states. I have placed this fairly heavy book on top of the box to keep infrasound out. And that makes a big difference. You can see the green trace coming here. I have to wait for things to stabilize. I have been running for about 1 hour with the book that prevents infrasound. And now I see the green trace here, 10 minutes of it, and it is rather unstable, but it seems that the on-off problem I have seen with the magenta trace is no longer present, or maybe here, but at a lower level. So I do not find it possible to draw any conclusion from this. Here is the waveform at the output. Now that the 20 MHz low-pass filter is not enabled anymore. So I have a saturation in the output amplifier. I can add a capacitor on the output transformer, 300 pf, like that. And I think this is better. I have decreased the input signal to not saturate the output amplifier, and then I get 3 volts peak to peak. What I see now looks promising. This is the Allen deviation, and up to 10 seconds it's fairly okay. It will not stay okay, because when I look at the phase difference here, you can see it is very strongly drifting. So I have to wait for it to stabilize. A restart after half an hour looks like this. You can see it looks like there is no noise from the amplifier up to 10 seconds. It will come if I wait for a while. What I see now is normal, because if I look at the phase difference, you can see it is very steep, and suddenly there is some noise here. While waiting for stability on the phase shift through the box, I can get an idea what to expect from the latest 12 minutes. I just stop here and then go to the edit and subtract the frequency shift. And then I see these instabilities, and I look at the Allen deviation for that, and this is what I would see. So this is what I can expect from the unit when it has become stable. We will see. Here is the noise I have seen, and if I look at the Allen deviation, here is what that looked like. So it's not quite as good as it seemed to start with, but I think this is still acceptable. I have moved the cable and I'm now looking at the limited output. And I will remove the first part here. And I have also removed the frequency drift. And then I see that the limited output looks the same as the output from the power amplifier. And then, of course, the Allen deviation is the same. I have put back the crystal and the feedback cable. So now the unit is an oscillator again. And you can see the red trace, channel 2 and channel 1. And here there is a significant frequency change. This is because the main door was open for a while, because I got the delivery of a new dishwasher. So it was open for, say, 10 minutes. And channel 1 is sensitive to room temperature much more than channel 2, which is only this little bit. Anyway, I have been running the PN2060 in parallel, and now I can see the phase noise of the Wenzel at 92 maybe already after 13 averages. So things work reasonably well, and I will try the new multi-crystal oscillator. I have moved the channel 2 oscillator to its ordinary place here. But when I connected it, I find that it jumps between 2 different frequencies, up and down. Not as frequently as it did with an earlier that you have seen, but occasionally. So while I hope that it will repair itself magically, I have connected the Wenzel oscillator instead. The multi-crystal oscillator is drifting fairly rapidly, I have the most sensitive scale that I have used before, 0.01 in this window. But you can see the noise seems very small and does not contain high frequency components. So both the Wenzel oscillator and my multicrystal oscillator are very low noise in the close range, up to 10 seconds at least. I have been running the PM2060 at the same time, and here you can see the offset frequency is 40 Hz for the channel 1 oscillator, while it is 3.1 Hz for the Wenzel oscillator. But the PM2060 does not need the frequencies to be very close to each other. They can be arbitrary. They just have to be stable. And the phase noise I see is rather interesting. At 10 Hz it is minus 156, but it hasn't converged yet. And at 1 Hz I see minus 126 or 7. It says minus 127.5. Then, closer to the carrier at 0.1 Hz, I see 90 dB. So that's not very good. It's related probably to the frequency drift. I don't know. There is a small curvature here also. I reduced the gain on the vertical scale by a factor of 8, and then one can see that the frequency drift seems to be very linear with time, and this spans about 1 hour, 3,200 seconds about.
This is 16 hours. I can see the noise down to 0.1 Hz, where it shows minus 93 dBc per Hertz, which is not particularly good, but it remembers the drift from start probably. Anyway, at 1 Hz I see minus 125.9, which is very good for 1 Hz offset, and 10 Hz minus 156.1, which is also extremely good. Then at 100 Hz I have this structure. I don't know, it seems like an interference. It could be because of the PM2060, or it could be something external. And the same here at 20 kHz and 100 kHz. These structures is some artifact, while the noise of the box is probably here at minus 188. Because of the long times, it is hard to do experiments to see what could improve a little bit further here. I need better reference oscillators. The Wenzel is better than any of my currently available oscillators. They have had mishaps and maybe never been good enough at 0.1 Hz. But at 1 Hz they have been very good, but no longer so. And that perhaps because I have moved the frequency significantly by about 37 Hz. The 13 Hz offset on one side to 24 Hz offset on the other side. The frequency drift of the difference between the Wenzel oscillator and my multicrystal oscillator, the red trace here, It has drifted about 1 millihertz over about 1 hour, and the variations here are very slow. So it doesn't contain things in the 0.1 hertz or even the 0.01 hertz that are visible here. I have a very narrow filter, and I have picked the channel 2 oscillator to display down here. I change now to display the channel 1 oscillator, like that. Then I wait another hour to see how that behaves. As it turns out, channel 1 has lost its locking, so it is sweeping up and down over about 20 millihertz. And when it's far away, the curvature here is fairly sharp, so it contains a signal at 0.1 hertz. It is 2 seconds per pixel, so 10 pixels means a significant derivative on the frequency. Now, not very often, and I can see that the imaginary part is about 10 decibels below the real part, so it hasn't destroyed the measurement. And of course, the vent cell is stable all the time, so this just degrades the imaginary part. The vertical scale is reduced by a factor of 10, so this is a huge frequency change as compared to what you have seen normally in this graph. I have changed the frequency and I wait for it to lock here. Now I made severe frequency jumps in the channel 1 oscillator, and therefore the result here has degraded. The imaginary part is up at the real part, and the real part is degraded. So the changes I made, they are not allowed. So I get rid of that, and I want to see what does the channel 1 oscillator look like when it is locked properly. And I have restored the normal vertical scale, and I can see how the green trace slowly will lock. Now channel 1 has locked, and you can see here it's far more noisy than the vent cell oscillator in a time scale of 20 seconds or so. But when I look at the PM2060, I have only one. Well, now it became 2 averages, and the noise I can see is minus 123 or so. And that is better than the vent cell oscillator. So correlation does something, even though there is only 2 averages. And the noise of this channel 1 oscillator is probably as good as of the vent cell at 1 hertz, although it degrades rapidly closer to the carrier. This is 1 hour and 10 minutes, and you can see how noisy my channel 1 oscillator is as compared to what you saw recently from the vent cell oscillator. Now, after this time, I can see the noise at 1 hertz. It says minus 127.8, but the imaginary part is not very much below the real part. I can compare with the previous results, which I have here. So the result is the same, but very noisy. But not here, at 20 hertz or so. So 1 hour 10 minutes is not enough for a reasonable evaluation. I guess the noisiness in channel 2 is what I can expect with this noise level from the amplifiers. So I will use the tiny PFA to try to make better amplifiers. But I will stop this video here, because after all, the result I have seen here with the Wenzel in one of the channels is very encouraging. Minus 125.7, or rather minus 126 if I look at the placement of the cursor. That is very low noise. I don't think there is something reported like that from crystal oscillators in the literature. When I look at the internet, searching for specifications of very low noise 10 MHz oscillators, this is one of the articles I find. Ultra low phase noise 10 MHz crystal oscillators by Jeremy Everard and co-authors. What they find is minus 122 to minus 123 dBc per Hertz at 1 Hz offset, and minus 148 at 10 Hz offset. And what I have now with my 20 crystal oscillator is minus 126 at 1 Hz and minus 156 at 10 Hz. So it is significantly better, by 3 dB at 1 Hz and by 8 decibels at 10 Hz. They give some references, and it seems that minus 122 dBc per Hertz at 10 MHz is about the best that is available, or crystal oscillators. In this article, 6 oscillators are being used to combine in order to get a lower noise floor. They report minus 182 for the flat noise floor at 10 MHz. That is 6 decibels higher noise than I see with my 20 crystals unit. Perhaps not so surprising, because I am using about 6 decibels more crystals, 20 instead of 6, so that is almost a factor of 4. The reported performance is at 10 Hz here, minus 150. And that is 6 decibels worse than the minus 156 that I can see. And of course, at 1 Hz, the combination of the 6 oscillators does not work well, so one can see only minus 120, which is the performance of a single oscillator. So what we can see essentially is a 6 dB improvement using 6 crystals. And that is valid all the way down to 10 Hz from the carrier. My brute force solution, using 20 crystals to get 20 times more power in the crystals, which is favorable for the signal-to-noise ratio. It is no longer the best way to get a very low noise from a 10 MHz oscillator. This is a fairly recent paper showing an optical method. This is from year 2013, so it's not the latest. But what they present is astonishing. What they report at 10 MHz is minus 145 dBc per Hertz. unprecedented phase noise levels, it is written here. But the way they do this is very complicated. It is dividing down an optical source. And maybe this can be done in less complicated ways in the future, or maybe already now. I'm not sure, I have seen the latest papers. But using crystals is fairly simple, even if you use many of them. So for many purposes, the optical route is probably far too complicated, and using many crystals could be a way of getting a little better than what is the standard today.